I think. Hello, everybody. For those who are the first time on Gaussian process webinar, you won't miss much because some of the basic principles of Gaussian processes will be slightly repeated in the beginning. For those who are already familiar with Gaussian processes, the introduction won't take a lot of your time. And in case you have any sorts of questions, there is a Q&A in the below where you can click and paste me any questions you want to address. And meanwhile, between the slides, I will go and look into that and try to answer to the best of my knowledge. And of course, there will be a dedicated Q&A after the presentation before we go to some coding examples. So let's begin. Previously, we talked about Gaussian processes for, in general, what are the kernel functions, what are the parameters, length scales, and so on. And this was quite good, but real-world examples include more complicated data structures like time series, and in principle, getting to know how to deal with time series helps you a lot in solving those applications. And the basic things you need to know about time series is that they include very special effects like seasonality. And seasonality is very common in a lot of data sets and processes. And usually it can be decomposed with an STL decomposition, which is kind of point estimate of what is treated as seasonality. So when you do STL, you specify what is the periodic part, like is it weekly, monthly, yearly, and you get a point estimate of the whole decomposition with the residuals. You can see this basic picture on the right. Here is the decomposition of CO2 dataset. And besides this point estimate, you won't get that much. If you have any source of trend and you want to predict this trend, you need to do additional steps that probably will complicate the whole research pipeline. So it's not really that flexible, yet it is very useful. And if you are limited in time, this would be the first thing you would probably do. With Gaussian processes, you're much more flexible in terms of what you can accomplish about the composition, about the effects, about trends, other variables or regressors, the error function. Many other things can be added into the building blocks of a Gaussian process. And moreover, you can estimate very important parameters like Lengthscales, which basically define how your process is stable in time. So to get this all, you need to go Bayesian and specify your model, adjust your hyperparameters and priors so that it reflects your domain expertise about your data. As an STL decomposition, the time series is split into 2 or 3 parts, maybe 4. And the basic ones are the non-periodic part. This is where trend goes, or other regressors that don't really depend on time, like periodicity and seasonality, but yet is defined somewhere else as an additional time series. So it's usually referred as a structural part in time series. The periodic part is the one that has all the seasonalities with possible granularities that are useful for the task. It can be monthly seasonality when something is repeated over a month, like buying something at the end of the month, like a subscription. Or it can be yearly seasonality when it deals with maybe business cycles or something similar. It can be weekly seasonality. Maybe customers are more active on weekends, less active on business days, and the Gaussian process takes this in account, where a repeated pattern over every week is like duplicated over the whole time series, and the model is trying to estimate what is this repeated pattern actually is. Holidays, other specific domain-specific events can be also represented as an additional input in the time series, which is actually very helpful if you deal with sales data, because there are holidays, they are of course tied to specific days, so specific that you need to take this in account as an additional input. And a small reminder for those who are first time with our webinar, and as a coincidence, it is the finishing series of the webinar. Let's just remind what is the Gaussian process about. So it is just a big, very huge multivariate normal distribution. Yes, the slides will be available after the webinar, and you can find the link in the main chat if you want to go into more details. And besides, and in this big normal distribution, there is a so-called mean function and kernel function. And the mean function, it is usually meant to have additional regressors, like linear regression from external variables, structural variables. It can be anything that contributes to the expectation of the observed variable. The covariance function, referred as K, is meant to figure out what is the similarity between time points. So if you are going to deal with days or weeks, it is going to say how similar week 1 is to week 2 or week n. And if the similarity is high, then the function is the time series will take it in account. In the non-periodic part, you can put growth models, linear trends, many of them, or change point models. And the basic idea is to represent the physical process of evolution of the observed variable over time. Maybe the observed variable saturates to some extent. Maybe it grows indefinitely with a linear trend. Maybe it grows exponentially because the without this min function, Gaussian process won't be able to actually figure it out for you and won't extrapolate nicely. So in order to model this complicated expectation over time and evolution of a variable, you need to think about your min function. Some obscure examples include change point models when there is a date after maybe there was an event when anything that was before and after can be treated should be treated separately. And in order to take it into account, you create additional parameters that are specific to those periods. There is a good question about min functions. So do you need a min function if you center and scale your data? Well, if you center and scale your data, I think you already implicitly put this min function in your data. So it is implicit in the standardization. But if you assume your process is stationary, that's it. I think you can go with just standardization. If the process is not stationary, I think you should still think about the min function, because you need to extrapolate and not just interpolate. Otherwise, Gaussian process is not used to the fullest potential. There can be many other examples of mean functions. They can be arbitrarily complex. So it's up to you to experiment with anything that sounds reasonable to a specific domain. So you're not restricted to just having something linear, exponential. As for holidays, I decided to include a brief idea about what you can do with holidays. Traditionally, holidays are represented as a Boolean mask over the time series, and if there is one, you get an event, you try to measure the holiday effect, and your holidays are distributed in time. Some holidays are longer than others. Maybe your clients act not just on the specific date of your holiday, but rather than in a period after or before the holiday. So the actual event is distributed somewhere near the actual holiday. And you can try to put this into the model, creating holidays with lags. If you think about it, those lags can be represented as a 1D convolution when weights are meant to distribute the holiday effect over time. And let's say you create such a mask that has exponential decay of the holiday effect. So people encounter a holiday, then change their behavior, and it saturates back to normal after some period of time. And what you can do is you can learn this saturation effect of the holiday event using Bayesian approach. Or maybe it's vice versa. People prepare for the holiday, change their behavior, and that's it. The holiday passes and they're back to normal. Both is possible to figure out with data. The periodic part is a little more tricky because you need to think about on different scales. You need to think about what happens throughout the year. Is there any pattern that shows a big picture? something repeated that doesn't necessarily depends on a specific month, but usually tied to some exact period in the year. Then you go down, look at maybe quarterly periods. Maybe there is a business cycle in the company. So in the end of the quarter, something magic happens, and KPIs or other metrics change exactly in the end of the quarter, maybe in the middle of it. And you can't refer to monthly effect or yearly effect. It repeats 4 times a year, and that's it. So if it is the case, then you can for sure add this periodic component into your model and try to measure it. Most commonly used are monthly seasonalities and weekly seasonalities. Those are usually periods when people get their salary in the same period of the month, in the same part of the month, and go to do shopping, spend their money, change their behavior, or weekly where people go back from work to weekends, also change their behavior, and this pattern is repeated over and over again. So everything that is periodic is relatively easy to estimate, unless you have a lot of noise in your data, which is yet another problem. But deciding what is signal and what is noise would be up to the model. And with sensible priors, you indeed can specify what you think is more important, which periodic effect prevails in data, and measure it accurately. When it goes to specify length scale parameters in the kernel, there is like a rule of thumb. There is just a consensus or preference, personal preference of what should be the length scale for week, month, quarter, or yearly seasonalities. And usually they're just it. For weeks, you get 3 days. For month, you get 7 days. For quarter is 1 month. For year, it is 1 quarter. There is like little to be more specific. Mostly, it should be like this. Of course, you can set up additional hyperpriors on length scale to estimate. But in principle, if it is a seasonal effect, it makes little sense to deviate that much from this point estimate. And it would only make model more complex and involves to estimate even more parameters like length scales, even though there is a good expert knowledge that for seasonal effects they can be set with just numbers. So in practice, you can go with point estimates unless you are very uncertain about this and unsure about these numbers. Now, let's look into how would it look like if we go to specify those parameters and length scales using periodic kernel in pymc. Well, of course, you need the same number of periodic kernels, their summation, as you have periodic parts in your model. But there is one missing thing that we need to add to the slide, and these are weights for periodic components. If you don't specify weights, you will have a kernel that basically treats the whole data set as normally distributed with covariance functions and variance 1 times 4. So it is some random periodic function whose variance is 4. To fix the variance issue, you need alphas for every of periodic component, and alpha weights your contribution to the kernel from a specific period. If you think that yearly seasonality drives everything, alpha, the biggest alpha, alpha 365 should be large. If you think that the yearly component makes minor effect, this number should be smaller. The same thing is for every other component. If you've been to one of my previous webinars, there was a lecture on R2D2 and 2 prior, which basically treats linear regression with R² and variable impedances. So this is exactly the case where the same prior can be used not for linear regression, but for time series and Gaussian processes. You can specify alphas with these prior, R2D2 and 2, and the total variance of the kernel on the prior would be just 1, or R². And all you need to do is to specify the mental model of what component is more or less important. And those alphas would be adjusted accordingly. An additional thing that is also very useful every time is to specify just structural trend component, the deviation from periodic part, because, well, in real world we don't have these patterns repeated like copy paste. They deviate in some way, and this deviation can be represented with an additional kernel, like exponential quadratic, and the observation noise can be modeled with yet another white noise kernel, which just adds a diagonal to the whole covariance. If we're back to apply this R2D2 framework, we would treat this whole number of vectors, alpha, every alpha and beta, as a sample from R2D2 and 2 prior, and the residual would be this white noise. It can be put into the likelihood or modeled separately. Let's look at how would it look like for the CO2 example. What we see, data looks pretty periodic with an exponent trend, or at least it looks like an exponent. So, but it could be also linear, and you can try different approaches to figure out what is the best growth model. But in principle, it should be exponential. If we were to do it properly, step by step, adding complications, one step stepwise. We first need to decide on the trend model, feed it, make sure that we don't mess up anything. And then after we figure out the mean component, we can add the periodic component. I'll use the exponential growth model. And if you take logarithms from both sides, you make this exponential growth model into so-called log-log model. And this log-log model is a nice approach to deal with exponentials. What we also need to think about is our priors. So we have to make such priors that we don't get black holes of CO2. If we measure density, we shouldn't go to some nonsensical negative low values close to zero. So there is some work and trial and error when looking into prior predictive plot. We need to just make an educated guess on order of magnitude of CO2 that can be possible on the planet Earth. And if we start with something naive and set up priors like on the left side, just guessing what they would be like, we see that in the prior predictive check plot, there is something that goes up to some astronomical number, and I can't even pronounce this number. And I just Googled how this CO2 dataset was collected, and it actually collects atoms of CO2 per million in volume of air. And if we get something that is 10 to the power of 1000, something is really off with this prior, right? So non-educated guess leads to a model that doesn't represent anything. Even if we think that the more data we put into the model, the closer we are to the maximum likelihood estimate, so we fix this bad prior. Well, this is not how it is usually done in practice. In practice, this non-educated guess leads to very bad results, very off results when you're with small data. When you try to make predictions, you're either overly optimistic or pessimistic. It doesn't give you a good picture of how should it look like. So the conclusion is simple. We need to work out our priors so we don't create black holes under prior predictive. And thinking out loud about what would be the growth model, we also need to put it into the framework that makes some sense. So what would be the growth over a decade, over the century, over 1000 years? How the emissions should evolve. And if we make some guess on like at least maximum allowed growth throughout the century, then we can put some constraints on growth prior. And this will help dramatically to constrain the model to work in areas that make sense. If you're about to work with something similar but related to customer behavior, Well, the same. Do you expect the sales grow 1000% per year? Well, maybe, but it's a common to, I think, in terms of smaller numbers. That's what our prior is about. And in this example, 400% in a century would be about this much per month. And this is already something. If we don't believe that CO2 can decrease in time, we can say the sensible lower bound to be 20% in century, which is this small amount per month. And with our monthly observations, this growth model is supposed to represent the range which makes sense for growth to happen. If we put into the normal distribution, it is something like this. So this growth is sampled from normal distribution with some yet obscure yet realistic parameters that represent our expertise about not creating black holes. Again, when it's something that represents real world and not nonsense. Under prior predictive, this starts to look way better. We don't grow to huge numbers. We started to cover data relatively well. And this gives a sense that with this prior, we can go ahead to estimate the posterior, because we already represent some physical process of CO2 to be growing in time. We don't go very off with our prior. And all we need is to compare our data, our mental model, and to figure out the growth parameter for CO2. If you try the naive model that doesn't take logs, we get some overflows, which are very annoying. So a good model would be to take logarithms again, as I mentioned previously. When we go to log-log parameterization, there is a special case where we need to think about epsilon and how is it represented in likelihood. So in log normal likelihood, epsilon is usually related to relative error. So if epsilon is 0.1, it is 10% relative error. If it is 0.01, it is 1% relative error. So whatever you think relative error makes sense, you should put it there. Under log-log model, our prior predictive slightly changes, but overall gives us the same picture. The difference is mostly due to these different epsilon error term. Well, and now we can indeed expect that our data and model can be sampled nicely in HMC. And indeed, we can go ahead and plot something to verify that we are very good at sampling. if we look into epsilon estimate, we see that epsilon is around 0.01, which makes sense. It is 1% relative error. Good. After we get the posterior plot, we can go to posterior predictive. When we had prior predictive, we validated our ideas and understanding of the model itself. In the posterior predictive, we make sure that we don't miss anything from our data. If there was a special effect in data, it will be visible in posterior predictive. So how good our model captures the data. And since we didn't include anything related to seasonality, it is not captured and it is clearly visible on the plot. So the next step would be to add seasonality to our initial model and work out the posterior. All right, let's get to some intermediate conclusions. Before complication step, we made sure that our model samples well, represents good domain expertise, and makes sense. And when we add yet another level of complexity, we don't break anything that was the ground for the seasonality model. For CO2 data, the only seasonal effect that makes sense is probably yearly. So we only have a single periodic kernel with 12 periods, 12 months, and with length scale 3. So it means that in 3 months, the changes are significant. And of course, we need to not forget the alpha parameter, which is the scaling factor for the whole kernel. Otherwise, our Gaussian process will not make any sense. In this prior structure for our kernel, we assume that periodic part is repeated like copy-paste, but it's not always the case. And the periodicity pattern can slightly change over time, and we need to adjust it. One way to represent that would be to use an additive part to periodic kernel. Another way is to add a multiplicative factor for changing seasonality. And let's sort it out. If we multiply the periodic kernel with exponential kernel, what we actually do is we say, well, this year, this century, my seasonality was with this pattern. When a couple of centuries pass, my seasonality pattern also changes. And that is how you can treat this multiplicative exponential kernel. And with length scale of 1,200, you say that in 100 years, seasonal pattern can change significantly. That's it. If you have any questions so far, don't hesitate and just ask them in Q&A. So let's look at how would it look like if we slightly vary this length scale for this exponential kernel? If we limit this length scale to infinity, our seasonal pattern doesn't change much in time. And that's visible on the prior plot. If we instead make this length scale to be small enough, we still observe some periodic oscillations, but instead of them being persistent, they change very quickly. So this is the whole idea of this multiplicative interaction between kernels. All right. So when we go back to our model, the thing that we get different, the thing that we add is our kernel and Gaussian process. And Gaussian process will have the mean function that is the same that we had before, but with the kernel, from what we've just discussed, with all this periodicity and century-long seasonal patterns. One thing we didn't adjust is epsilon term. If we don't think about epsilon, on the prior predictive plot, we see some noisy time series. And if we think more about that, our epsilon can dominate all the seasonal patterns. So whatever you observe can be treated just like noise. So epsilon shouldn't be that, shouldn't allow these oscillations to happen. And in order to enforce that, we can change our prior about epsilon to be more informed towards less magnitude of observational errors. And yes, if we measure CO2, we measure it with high precision tools. And if we get the world model quite well, everything else on top of our model would be the observational error if we don't miss anything. But it's impossible to take into account everything, and this epsilon can be sometimes significant. If we don't use any approximation tool to fit the Gaussian process, and there are plenty of models that can approximate Gaussian process quite well. All we can do is to use phi and ma without any posterior predictive. And with the Gaussian process, we can make extrapolations, interpolations, whatever we want on the time domain. But let's find out how we can use Gaussian processes more effectively in practice. So in order to use them, we need to make them faster. And can we do that? Sure. So some words about the model that we just fit with the Gaussian process, with the seasonal component. So the learnings should be that in a seasonal component, you can not only specify the seasonality pattern, but you can also specify how the seasonality pattern evolves over time, and if it even evolves. It is done with a combination of periodic kernel and exponential kernel. And in order to add this additional complexity, we first worked out the linear part of the Gaussian process, so the mean function. The next cool example about Gaussian processes is that they can not only represent observed variables, but latent variables. And a great example there is stochastic volatility. The stochastic volatility is inspired by Bayes alpha model from Quantopian. And the latent factor is variance of returns. We don't observe them explicitly, but we observe them to influence on observed returns, daily returns in stock exchange data. And with the Gaussian process, we can, like a sliding window, estimate this volatility over time. And with stochastic volatility, sliding window is okay to estimate this volatility changing in time. But there are a lot of models where this time-dependent latent parameter is hidden very far from observed variables, so we can't even think about sliding windows to make a guesstimate. But let's find out how to work out this model into realistically estimated and rigor mathematical model. And the key idea is to decompose the whole model into assumptions. And what we need to assume is first that returns are constant. It doesn't make much sense to invest. Well, in some cases, it indeed makes sense to treat returns to be non-constant, but we need very long-term series and very strong assumptions on how should this return evolution behave. On this data, I try to validate this hypothesis, and to be honest, the hypothesis was not really supported. So let's treat it as constant. Volatility is, as we observed above, doesn't seem to be constant in any way, so we should model it somehow. And the easiest yet flexible way to do that is using Gaussian process. And we can use approximations to fit this model very quickly. And so we can do this on GPUs. These are basically matrix multiplications happening over and over again to compute gradients. So we can utilize GPUs to do this slightly faster than on paper. Another important thing are priors. And again, I highlight how important it is to think about priors when you deal with real-world data. So what about returns? Do you have a brief idea what would be your portfolio in a year or two, or maybe in 10 years? Can it grow 10 times or 100 times? Well, doubtfully. So I think it is realistic to either have the portfolio doubled or zeroed out in a year. Well, anything can happen. So this brings us to the daily return to be computed as following. So we take this 100% growth and get a square root of number of business days. Do some mathematical magic to calculate a single number. And here we are with a mean guesstimate of a daily return. Maybe this prior assumption of this beast growth or dramatic loss is unmotivated, yet it is very, it is way better than making really random guess on daily returns. As for volatility, I think a reasonable assumption is to say that signal to noise ratio when we deal with markets is somewhat 1. So we can't say that if we see return in a specific day to be high, that our that yield increases. So we can really make any guess. And that leads us to the ratio mean to standard deviation to be around 1. And in practice, that is something that usually referred to market efficiency when it is impossible to figure out the prediction for the future return on business day. So logarithm of standard deviation should look like this. Same as daily return, but on the logarithm. Before we go to the time component, let's paint a big picture. And the big picture is to get those returns, logarithm of standard deviation, that are like mean mean over the whole period. Then we'll go to the Gaussian process part. And here we think about how does volatility change in time. And if we put length scale to be something like gamma with mean 30 and standard deviation 5, then we say that volatility changes dramatically only after month has passed. Otherwise, we can't observe volatility change. So means that we don't observe volatility to change instantly the next day. But we should also specify alpha for the time component of volatility. And since we're dealing with logarithm of standard deviation, and remember I was talking about logarithms and epsilons. So epsilons, and in this example alpha, it is treated as relative change. So if we scale our kernel by alpha, it means that the variation on the relative scale of our standard deviation should be square root of on average, this exponential is 1 by 100, so square root is 1 by 10, 10%. So it's about 10% variation around the average logarithm of standard deviation. Right. Instead of exponential kernel, I decided to use Martin 32. And that means that it is slightly less smooth compared to exponential kernel. So that allows more smooth changes, less smooth changes of volatility. So that's the big picture of what happens with the latent factor of volatility. And when we put this to observations, we have some returns. These are common across the whole period. And instead of standard deviation, we put the exponent of the time varying part. So it is mean plus the variation component over time. So it's delta t. So errors are correlated across the whole period. And not only errors, but the magnitude of errors is correlated over the whole period. Number of days in the whole period is huge. So when we go through this whole model and work out the Gaussian process, the covariance matrix is huge. And if we don't use any approximation or optimization over the Gaussian process, we just wait a couple of days and see how it goes with sampling, then go take another cup of tea. Well, to make this faster, we need to think about how to make an approximation that doesn't break anything. And recent addition to pymc is HSGP Gaussian process. Let's find out what is this beast, how can it improve your Gaussian process analysis tool and modeling approach, and how can it help with our example. So HSGP is translated as an abbreviation of Hilbert space Gaussian process, HSGP, and it works in Hilbert space domain, and Hilbert space for babies is function space, and one of the examples of these function space are harmonic functions. If you look at the picture on the right, you see those periodic functions with decreasing period length, and an infinite number of these periodic functions can create a basis for the whole functional space. So any function can be represented as an infinite sum of those periodic functions. While it sounds really crazy, those harmonic functions and bases in the functional space for many sorts of functions can be really sparse, and we don't need this infinite sum. And that's the whole idea that is utilized in Hilbert space Gaussian processes. To be more specific, this approximation doesn't work for any sort of kernel. It works for only for stationary kernels. And it is really tricky to do this for periodic kernels because they don't have the fancy closed form solution to this approximation. But there are practical ways to overcome this constraint. In terms of complexity, a traditional Gaussian process is n to the power of 3, so it's cubic complexity. And if we have 1,000 time points, well, you can imagine how huge is our matrix that needs to be inverted. For HSGP, the complexity is just like a dream. And this dream is almost linear complexity in terms of time series length. So it's m by n, where n is your time series length, times and m is number of basis functions. It's number of those function space basis functions that approximate you the whole domain. So when we move from cubic complexity to almost linear complexity, there is a big difference. And we can even sample on CPUs for the whole time series. Sounds very fun. There are some parameters that still need to be elaborated on in this HSGP approximation. One of them is the extrapolation boundary. So the approximation doesn't work on the whole real line. It only is valid within the extrapolation boundary. And a practical way to fit HSGP to data is to center the time dimension. So you have negative time, positive time, 0 in the middle. And this L covers the whole period that you want to explore. So if you want to make a prediction 2 years ahead, make sure that this extrapolation boundary covers the whole region. And M is number of basis functions that is used to approximate the whole thing. The larger number you use for M, the more accurate is your approximation for the whole Gaussian process. But it comes with slightly added computational cost. A starting point for M, which usually makes sense, is 30. But sometimes you can make it larger. But I find 30 to be good enough. Maybe you can try 60 or 100. In most cases, that won't make you a huge difference, but sometimes it's more helpful. But when it's compared to cubic complexity, yet you still have this huge difference. So the more complicated your function is, the more basis functions you should use. The only thing we need to change in the previous model is to replace Gaussian process with HSGP, and that's it. And our model will sample not in 1 week or 2 weeks, but just in some reasonable time, maybe 5 to 10 minutes on GPUs or CPUs. Even CPUs, we will see that are great for getting things done. Right. I think that's it for time series and how they can be accomplished with Gaussian processes. If you have any questions before we go to our coding session, please post them on Q&A and make sure I will answer. Right. If you don't have any questions, we now go to an interesting example from pymc that previously was a rolling regression example with Gaussian random walk prior over the parameter, but it makes little sense to have the rolling regression of this kind. Let me prepare the notebook and share the screen. Good. So wait a minute. Good. You should now see the entire screen. Let me make sure that it's correct. I'm sorry. Good. So the rolling regression example. So in pymc examples, there is a fascinating case study about rolling regression. You can find in gallery. And this rolling regression assumes that you have prices, gold prices, and index for gold extraction cost, and they are connected. So the greater cost is for extracting the gold, the high price should be paid to buy some gold in stock exchange. And this relation changed in time, and if plot them against each other, we can indeed see that index versus price is not linear dependence. So this linear dependence evolves over time. So you can see the shift, the obvious shift in this linear regression. So if we worked with the period in 2014, that is very different from the period from 2010. And the basic model used Gaussian random walk, which has some drawbacks. So in Gaussian random walk, you don't have a stationary behavior of coefficient. So you don't treat it like oscillation over mean dependency. So it's rather wanders around in an uncontrolled way. So one way to improve this model is to replace the Gaussian random walk with Gaussian process. And this Gaussian process is very powerful to make this model sample quickly. And as I said, CPU can be really powerful, so we don't need GPUs. We don't even need GPUs to sample. So I won't use my GPU to run this example. So there is a question on Q&A. Missed few means of the presentation, but I was curious, what would be the difference between general time series approaches using prop-het versus using GPs for time series in terms of interpretation of results? Well, in prop-het, Gaussian processes are still used, and prop-het makes really good assumptions on the structure of the time Gaussian processes for time series, so taking into account all the holidays, possible seasonal effects, so it can be really powerful for generic time series. So prop-het is not bad. You can use it if you need to make predictions. And if the sole purpose is to make just good predictions, I think prop-het is the way to go. If your task is a bit more involved and you have latent parameters that evolve in time, prop-het, so you can't use prop-het or any other prediction model to estimate latent parameter because there is no target. So it's not possible to make an estimate. So in terms of interpretations, it's the same. You can go into prop-het internals and find Gaussian processes. In terms of results and outcomes, kind of the same. And GP is a building block. Well, so let's use CPUs and get some data. So the basic linear regression model samples in 3 seconds. So it makes 0 sense to delete this cell to make the workflow faster. So in order to satisfy the curiosity, let's plot the basic model against the data and make sure that we indeed have similar results to what was in the case study. Great. For rolling regression, we had the dependency, which involved Gaussian random walk. And we're not going to do Gaussian random walk. Let's comment it out. It will be useless. We could do something more fancy. So, and something more fancy is to create a helper function. And this helper function will use an advanced nested model API. If you don't know what is the nested model API, so it's basically a name prefix for all the variables you create in a nested context. So it would be name sigma, name mean, name length scale, and you can ignore any complexity in doing it manually. So you define something you can do repeatedly and instantiate the Gaussian process for each of the variables. So in our example, how would we interpret this sigma, mean, and length scale? So mean would be the average behavior of our dependency between producing index and the gold price. Sigma is the deviation over time, and exponential 50 would mean that the coefficient can change, like standard deviation of the coefficient in time would be 1 by 50. So for length scale, it is 1/4. So in 1/4, the dependency can significantly change according to what is sigma. If sigma is 0, the significant change is 0. So you can also play with specifying coefficients for sigma. And the R2D2 M2 framework is exactly about that. You can have arbitrarily complex Gaussian process, but if you have the sparsity inducing alpha and for the kernel, you can exclude it from the model completely. And the model would decide if it is essential to keep this or it should be dropped. The rule of thumb for 30 basis points, C parameter is similar to L, but it is a multiplicative factor for input, and input is the integer time. So and our integer time is from -500 to 500 something. So it's about 1000 time points. Obviously, the mean function is constant. We don't assume our dependency deviates in some sort of way. And I think we can really interpret every of these parameters. So does the dependency change over time? How much does it change over time? What is the average dependency? Well, everything is pretty interpretable. And when we finish with the model context, nested model context, we instantiate the Gaussian process prior and specify the same name as the context. So we can really address every of the nuance parameters using a nice API. And there is a question on Q&A. So I'll just read it out. Hey, thanks for the great talk. Are there any examples of using latent GPs or HSGPs, for that matter, for logistic growth models you discussed briefly at the start? Oh, yes, sure. So one of the great examples that can be found on the internet is pymc labs. Yes, modeling changes of marketing effectiveness over time. So for HelloFresh client, in pymc labs, we build marketing model where customer acquisition cost changed in time. So it is a valid assumption that the customer acquisition cost will change maybe according to some seasonal factors and observed factors. And if we don't take it in account, we can get misleading results. So we get some average estimate, but it won't mean anything. Maybe in reality, we had the decline in customer acquisition cost that we can utilize, putting more efforts to marketing, more budget to marketing. But since we are estimating average customer acquisition cost, we don't make this decision. And vice versa, to avoid overspend, we can track our customer acquisition cost to grow or decline, make actionable decisions. So in this particular model utilized HSGPs to their fullest potential. So this is the complicated thing you can do with Gaussian processes that can solve some real-world tasks. Back to our simpler model, but yet it is very representative to what was happening in mixed models. We have a latent parameter that changes over time that we need to figure out to make something out of it. And we define a Gaussian process changing coefficient linear regression. And we sample it with NumPy. So if you don't know what is NumPy, it is an awesome library written in Rust that is used together with pymc. It is built by one of our principal data scientists, Adrian Seibold, in Rust with Python bindings. And it's very fast. So it is that fast that it will sample the whole model with 1,000 time points in just a few minutes, 5 minutes. And it translates the model to C++ using number. And with the number, you can vectorize like beast. And I didn't believe that this model utilized the whole tiny supermicro with 60 cores. Like, it was full juice, like full juice of 60 CPU cores were utilized to sample this Gaussian process quite fast, just on CPU. So on GPU, it was slightly less. It was not that fast, but due to the size of the Gaussian process, it really scales when you have a bunch of multi-output Gaussian processes. And that's where GPUs make the model even more faster. And the model is actually quite tiny, so all efforts are put to store the samples in the trays. So there is more overhead than actual work for the GPU. So that's why CPUs are better to work out this specific example. Oh, let's try both. We have 5 minutes, and I can actually spend a couple of more minutes to run JAX. So that's not an issue. Let's try. I have set up both. And let me find out. Yes, I will use the CPU version of JAX sampling. So when I decide whether to use NumPy, JAX, GPU, JAX, I make a couple of runs, like 5 minutes long, 3 minutes long, to figure out the expected time to complete the trace, and then just run the one that is the fastest. So right here, NumPy was kind of okay, and I was impressed by CPU cores consumed to the full juice. If you have any question while MCMC is sampling, we can have some nice discussions. And of course, if you have any sort of ideas on maybe your problems, your applications that can drive your business, you can reach me on LinkedIn, send me an email, and reach me on any social platform, and we will find out what would be the best use of Bayesian methods for your problem. If we don't have any questions, we have 2 minutes break, and I'll get some water. All right. So let's do some quick visualizations. Oh, this is a nice question. How would you specify a multi-output Gaussian process that has a lower rank structure for latent factors? For example, we have a Gaussian process that drives 5 variables, but those 5 variables can be clustered into 2 or 3 groups. That's an involved question. I would output a low rank structure, like the basis, decomposition for those variables, and then reconstruct the whole vector of 5 variables out of the low rank representation. So if it is decomposed into 2 or 3 groups, it is 2 or 3 basis functions. So you learned the basis decomposition and three basis vectors. So in time series, you predict the matrix 2 by capital T, and the basis matrix 3 by 5. So 2 matrix multiplications, and you reconstruct 5 variables. Something like this would be a nice try. Good. Let's visualize what is the dependency for our coefficients alpha and beta. So we see that alpha evolves over time. That is very cool. And same for beta. That is also nice. So beta is our slope. And we see how slope evolves in a very nice way. If we're about to plot the whole dependency over time, we see all sorts of lines going through data. So, and colors match the time periods. And there is a very interesting dependency. Let's do the final comparison with JAX. That would be an entire sample. So we vectorize the computational graph and try to sample. It should be on CPU. Oh my God. Ah, I had a typo. That's better. I thought we were using GPUs and I got CUDA error. And CUDA errors, always fun to debug. I love CUDA errors. They bring joy. Well, I think it's pretty close to compare. So 8 minutes. So it should adopt, fit the mass matrix, and then we will observe a speed up in sampling. And meanwhile, let me check my HTOC. So it seems one CPU core is doing the whole job. Interesting. what we're doing those 60 cores when I was sampling with NumPy. Well, I think NumPy is faster for this example, indeed. So let's try non-vectorized method and finish this. So maybe we sample with 4 cores instead of just 1, we observe some speed up. Let's find it out. Oh, I think that was the reason why I switched to NumPy. So this huge progress bar is very fun to track, but it is faster. And it's a nice experience to keep track of it. Right. So the conclusion. And let me check if it's really 60 cores doing some job. Well, I think that's it. We can finish, stop the recording. So the thing I'm curious about